Hello and welcome to the lecture Image and Video Restoration. In this lecture, we are going to discuss the various aspects of image and video restoration. First, we introduce the concept, then we start discussing image and video restoration application like single image derendering, single image dehassing, video derendering, and different application areas. Then we discuss spatial domain approaches for image restoration and image restoration through the swing transform. As we have understand that image and video restoration in one of the major computer vision task which is essential for our daily life or even research and industrial applications. Now we can say that images and videos are graphical representation of our everyday life. So from a human eye, that there is some object or scene that we wish to remember throughout our lives. Not only that, there is a very important application like remote sensing, medical imaging, and many more, where if the images or videos are being corrupted or being some noise become very noisy, then the corresponding downstream tasks like classification, object detection, semantic segmentation, and so on are becoming very tough for that. So it is important that there should be some mechanism that restore or denoise. Actually, restoration thing is basically a wide term. Under this umbrella, lot of image processing or image or video improvement task is defined. So why this noise? One reason definitely the natural noise. Other thing, maybe there is some sort of operation, like just for example the JPEG compression. JPEG compression, there put some noise. So can it be possible to denoise it? Other different computer vision or image processing task which may add as a side effect to some noise or any other communication noise, some sort of other kind of corruption that corrupted the image. Somewhat if there is something is coming that some portion of the image is getting destroyed, then some image inpainting kind of requirement or some sort of restoration is required. So as a whole, what we have understand that given a noisy image, there is a lot of requirements and it's very important for restoration or improve the. So in this lecture, due to the time bound, we use this restoration term. So we generally use under this some different computer vision where the image is getting improved and so on, this kind of task. Okay, another important thing that we should consider here at the very beginning of this, that the underwater image improvement or restoration. So there is in underwater things has been much challenging because there is a lot of different aspects and there is a lot of noise or impairments is very natural. So for this kind of application, that let's say if we say that the semantic segmentation of underwater video or image or object detection or localization kind of problems. And most importantly, object tracking in video in underwater scenario is very challenging. And in these situations, image video restoration become a very handy tool, or this makes the research is very important in this domain. So first we have to understand that from the perspective of the research and application, that how this restoration is helpful. Just for example, here you can see that there is a normal image and that is a foggy image. So in this adverse weather condition, this is foggy. This example is basically, it's very hypothetically it is foggy, but it may be rainy, may be hazy, may be snowy and something like that. So it may be profoundly challenging for an autonomous vehicle to figure out what lies ahead. So that is very important. So one thing we understand that here the steering angle is minus 70, but it becomes steering become minus 60. So the thing is that this kind of noisy images or videos make the downstream task challenging. So if we can have a tool or a procedure so that we can get back this original or the very near to this original image, then things will be rather improved. So what is important, that the necessary to remove this noise to restore the visual quality of the degraded image and videos. But it essential make this image video restoration nowadays is very important research and industrial application. So same as the video restoration enhances the sequence of frames. One thing it is important, that whatever we have said, we are saying that it is basically the restoring the spatial quality. But when we are restoring a video with the spatial quality, in parallel we have to maintain the temporal consistency. So if we set only frame by frame, that considering a particular frame as an image and improve it, that may not give you a very smooth video. Okay. So that is also an important thing to consider. So as a whole, what we understand is that image and video restoration is a very important topic of this date. Now we have to find out what we basically mean by. Now given a noisy image or video, if we say just a very simplistic mathematical, this is that 3-dimension, it's the RGB. So it is a pixel values. And restoration aims to estimate the denoised image or video YC. So YC is basically a sum function of Xn, where this C, Mn denote the channel spatial dimension of the image. So M and N spatial dimension is the channel. Channel is for a RGB image, this is the RGB, so 3 channels. So this is the basic idea of this. So what we have to find? We have to find this F. So that given this noisy image, we get back this original or near original images. Now in this image video restoration, there is a different kind of task. Okay, so image video deraining, defogging, dehazing, these things are very similar, but there is a certain difference as well. So this is enhancement, super resolution, deblurring. So these are the different. So it is not possible for this course to the sets like everything. So we choose something, some of the topic, and at least try to understand what this mean actually. What do we mean by, and what is the general procedure, and what are the basic idea. For understanding the thing, we start with non-deep and very naive spatial domain approaches, and then we'll show that is a very advanced transformer based approach to understand that how restoration is being taken, or this problem is taken, and there's a lot of research, lot of very good solution been provided. So the first thing is single image deraining. In single image deraining, the problem is that we have given an input image x, xn, that is a noisy image. So this is xn. You can see that this image, there is a rain is there. So what is the objective here? We have to find out this image without these rain streaks. So the basic idea is that the goal of single image deraining problem is to estimate the derained image given a noisy image xn. So xn has a noise image, means it's a rainy image, or there's rain streaks is there. We have to remove these rain streaks. So one may model this above relationship as xn is equal to rs plus yc. What is rs? Rs is basically rain streak map, and this rs is added with the actual image, the denoised image or original image, and we have to get back this by this reversing equation xn minus rs. It is a very simple kind of understanding, and this image is of this dimension. That is this is channel, this is the image resolution m by n, the size of the image. This is as a whole, and this rs is basically the rain streak. It looks like this. Now the question is that where the challenge lies, that is a single image is given, because if there is a multiple image given, that and the pattern, hypothetically if we consider the raining pattern is same, that just by averaging we can get the raining pattern, and if we can get the raining pattern, we just this we can take this subtraction and get back this y easily. But here the problem is that this is single image is given. Generally we are trying to do it by learning based system. Okay. Now the next problem is single image dehazing. These are more or less similar problem, but here the noise patterns are different. It has been expressed in this different way or represent different way. Now here one thing, that the transmission map is going to be involved or is important. So there is a two thing. One is transmission map, this is TM, the similar dimension of this image, and another is called global atmospheric light, that kind of light present there. So with these two parameters, now this xn, that this hazy image is basically represented in this way. Then yc, that is the actual image, into this T of m, this transmission map, plus L of A, that is this basic transmission, this global atmospheric light, 1 minus T of m. T of m is this transmission map. So this is the basic representation of the hazy image. So the transmission map Tm is exponentially varies with the depth of the pixel p, and can be written as this T of m, this is e to the power minus beta to d of p, where d denotes the depth map and b is the scattering coefficient. So it's basically they are trying to find the scattering effect of this light, because in haze light is scattered. Sometimes very non-technical you can say some diffused light. Okay, so that we have to take into consideration. So this is the normal representation of this. Now what is our job? Our job is that given the hazy image xn, the task of single image dehazing aims to recover the clean image by itself. Just what we have to do, you given this this particular representation of hazy image, we just do the reverse thing. X minus L of A 1 minus T. This is just we took this. But the problem is this is not whatever, this is a very easy equation and we put it the values and get back the non-hazy image or clean image. It's not so easy. So the thing is that this is a clean image, this is the hazy image, and this is the atmospheric light, then this is a transmission map. So, and this the way we can make that, but it is not that these all things are present and just put it. Sometimes it is very tough to not get the result. So that we will see in our these single image imaging problems learning, and so that how this can be done. Although we are not going to discuss all these things in this, but we have to give one thing that how actually things are being done, and in a very kind of similar way we can get this kind of de-hazing problems. Now again, next comes the video deraining. Now video deraining, one thing is very important to understand. If we consider that each video frame is basically a single image, then the normal image deraining can be easily applied. But there is one problem, that what we have mentioned earlier, that if we do frame by frame by using the image deraining algorithm, then there will be some temporal inconsistency come to play. So it may be in video the object is moving, so there is some movement of the pixels, so we can say optical flow or all these things. There is some temporal motion in there, and sometimes if we put this kind of frame by frame operation, it can lose this temporal consistency. That you have to keep in the mind. So here, so how can we define this? Is VC denote the rainy and its corresponding clean video respectively. The mathematical formulation of this video rain streaks in the video can be expressed as this. Now this I is a particular frame, okay, RS, where this denotes the ith rainy rain streak map and clean videos respectively. So this is just the understanding or representation of the problem of this kind of deraining, dehazing, and in video domain or image domain. So what we have seen, that so many problems that we have understand the problem. Now how to solve it, that we'll see later. So what are the applications? Applications are lots of applications. Something we mentioned here, autonomous vehicles. Nowadays autonomous vehicles is a very emerging field. So autonomous vehicle may require images and videos to be rain or haze free for an efficient traffic sign detection, vehicle tracking, or scene understanding. That we have already understood previous discussion. Next comes the satellite imaging. Improving the visibility of the hazy and cloudy satellite optical images for an efficient spatial feature extraction like road, land, and forest. So you can say that it is very understanding the satellite image, this video restoration or image restoration board. Underwater navigation. So visibility enhancement and de-hazing of degraded underwater images may be result high-level vision task, because in underwater there is a lot of aspects are involved, so that we can take into consideration, such as object detection, semantic segment, etc. Outdoor surveillance and tracking, that is also another important field, that improved visibility can also be beneficial for outdoor surveillance and tracking. So these are the very only 4 we have pointed out. Many more application for nowadays image video restoration is a very important research and tools is required for the better performance of the computer vision task. So we start with the spatial domain filtering. that spatial domain filtering are basically used for image denoising. Although it's a very straightforward method, but to understand the essence of this image or video restoration or denoising, it's a very good way or very simplistic way to understand how the process is being developed of this denoising or these restoration techniques, these processes. So start with mean filter. Now mean filter essentially is that take the average value of the neighboring pixel. So this is this value we detect this average. It's very simple implementation. But the problem is that it blurs the image edges. So that is, you can see here that you can find that this image edges and image itself has become blurred of this. So there is some sort of noisy image, but it denoise it, but there is some blur. So it's a very simplistic approach. Next thing is median filter. Median filter replaces each pixel with a median value of the neighboring pixels. So the median of this. Okay. So this is the way the median filter works. Given a kind of kernel size of this kernel 3 by 3, this the median value of this will be replaced by this. This is the point of under consideration. It is very useful for denoising this saltpeter noise. This noise like saltpeter noise, this median filtering is used, but it preserves edges. This edge is not. So median filtering is another very simplistic approach that is we can use for the noising. More frequent approach is Gaussian blur or Gaussian filtering. So a Gaussian filter is a low pass filter used for reducing the noise. Noise means generally what we think that noise kind of thing is basically random in nature. So if any random thing is basically is considered that high frequency component, if you transform the image, so in frequency domain, noise lies in the most of the high frequency zone. So what Gaussian filter do, it's a low pass filter means that high frequency components are being excluded, but it essentially blurred this blurring effect as a whole will come to the, because high frequency component basically give you the edge information properly, where this certain change of pixel values. So this is somewhat blurring. It is useful for very this image denoising, but at the same time it's basically blurred the image. This filter is an odd size symmetric kernel that is converted with the image. So this is basically to understand, and this is the kind of expression that is basically very well known Gaussian expression that g of x y, this you can say x coordinates, and this is 1 by 2 pi sigma square, that is the sigma is the standard deviation, and e to the power minus x square plus y square by 2 sigma square. So this is a very famous or very frequently used Gaussian these Gaussian equations and normal equations. So the kernel weights the highest at the center and decreases as moving towards the periphery, and it is very easy to understand that the standard Gaussian curve. So this makes the filter less sensitive to the drastic change that edges, allowing a smooth blur effect that we can understand. Okay, and pi is basically constant. So this we can is called the Gaussian filter. So in this way we can do some spatial domain kind of filtering. Although it is just a very simplistic approach and non-learning based approach, we are essentially going to understand the learning based approach, where this deep learning or before that machine learning. So here you can see there is a lot of approaches been used in this image restoration from the deep learning point of view. CNN based approach, generative adversarial network based approach, autoencoder based approach, transformer based approach, diffusion based models, and so on and so forth. So here it is not possible for us to discuss all these models because these are the typical research trends of this. But for understanding the situations that one transformers models we are going to understand. So it will give you some idea that how actually deep learning techniques being implemented or utilized for image restoration. So this we first introduce here a typical transformer called Swin transformer. The Swin transformer is a hierarchical vision transformer. So VIT that we have discussed in detail. So it's a hierarchical vision transformer, and in this architecture they use the shifted windows to compute self-attention locally, achieving the linear computational complexity relative to the image size, and that is one of the major characteristics of the Swin transformer. So it acts like a versatile backbone for the computation tasks, including classification, object detection, restoration, offering high efficiency and superior performance over the traditional transformer model. So this Swin transformer is a kind of input over the normal VITs, specifically for downstream this vision task. Now let's see what is Swin transformer. This Swin transformer, this figure A, this Swin transformer, this is a normal VIT. This builds a hierarchical feature maps. You can say this is the hierarchical feature maps. It's basically this feature maps by merging image patches slowly and showing in this gray thing, this kind of thing. These patches in deeper layers and has a linear computation complexity to input image size due to the computation of self-attention only within the each local window. So each local window here they are basically computing, and then so what it is basically doing, they are basically merging the image patches. So this in this way, this to 4 into 8 into 16 and so on. So these are the small image patches. So this is the 4 by 4 patches, and then it is 8 by 8 patches in 16 by 16 patches and so on. So small patches we are considering. So this merging image patches in deeper layers and has linear computational complexity. So it can thus serve as a general purpose backbone for the both image classification and dense recognition task. So that is very interesting thing. So I repeat, it can thus serve as a general purpose backbone for both image classification and dense recognition kind of semantic recognition. But how it is different for the traditional this vision transformer, which produce the feature maps in a single low resolution and have a quadratic computation complexity in normal VIT to imaged input image size due to the computation of the self attention globally. So here it is hierarchical, so it's a linear computation complexity, but it's a quadratic computation, so it's a linear, it's computationally less. So now how image restoration is done using Swin transformer. So the image restoration model, namely the SwinIR, is based on Swin transformer. First, this particular model we discuss, we try to understand what is this. The SwinIR is basically 3 modules, has many modules: shallow feature extraction, deep feature extraction, and a high quality image reconstruction module. We'll see this is basically the shallow feature extraction, deep feature extraction, and this image reconstruction, this high quality image reconstruction. So this major module. Now here you can say this is a series of RSTBs, residual Swin transform. What is basically this? Shallow feature extraction, this kind of thing is there, and after that deep feature extraction, and deep feature extraction is this basically. Now again come this shallow feature extraction module uses a convolution layer to extract shallow features. Okay, which is directly transmitted to the reconstruction module so as to preserve the low frequency information. That you can see that it is coming here. So it basically, this shallow feature is using this. That shallow feature is that what? It preserves the low frequency information. Now deep feature extraction module is mainly composed of residual Swin transform RSTB, each of which utilize the several Swin transform layers for local attention and cross window interaction. Okay. In addition, the convolution layer is added at the end of the block, the feature enhancement, and use a residual connection to provide a shortcut feature aggregation. That's what we are seeing here. This is this residual block. Okay. Now this is the Swin transform layer, this STL. Now this STL is basically a series of STLs there within each of these RSTL. So this is this layer normalizations MSA plus Neogen MLP, and this way it is. So finally, both the shallow and deep features are fused in the reconstruction module for high quality image reconstruction, so that we can this particular features and this shallow features is fused to reconstruct the high quality image. So this is the transformer module of this. Now this you can say the result, you can say this is the previous approaches, and you can guess it is the Swin transform module, and it is a very good. You can see at least that the quality wise it is good. So in this lecture what we have discussed, that image and video restoration. Under this we introduce the concept, then we try to understand the different aspect of video restoration application, like image deraining, single image deraining, single image dehassing, video deraining applications, and then we try to understand spatial domain approaches for image restoration and image restoration using Swin transform. Next lecture we will discuss the medical. Thank you very much.